So today we're going to put 5.1 through 5.3 together in our notes, and it's because the definitions all kind of go together. So we thought it would be easier for you guys to just organize your notes with all the definitions together. So we're going to first start off by filling in this table. So if you want to pause the video and go ahead and make this table in your notes, and go ahead and label each of the rows and columns. Go ahead and pause the video, get that done, and then we'll fill it out together. Okay, so the names that we already have listed there should look fairly familiar, and then the rest of it will kind of be newer stuff. So we're going to draw some pictures, we're going to write definitions, I'll give you those special properties, and then we'll practice it. So a perpendicular bisector. Before we had a perpendicular bisector that met with a line. Now these are all going to be inside of triangles. So our perpendicular bisector and triangles, we have two pictures for it. When you have a perpendicular bisector, you can have it drop straight down from the vertex. Remember, the vertex is a corner of the triangle. It's where the angle forms. And a perpendicular bisector will meet at 90 degrees and cut the opposite side in half. Now, if the perpendicular bisector drops down from the vertex, we know this is an isosceles triangle, so these two lines would be congruent. The other picture that we have for a perpendicular bisector does not drop down from the vertex. So it's just a line that cuts a side in half and meets at 90 degrees. So either of those pictures can tell you it's a perpendicular bisector. What you want to focus on is this bottom part right here. If you see that it meets at 90 and cuts the side in half, then it's a perpendicular bisector. The point of concurrency is if we draw all three perpendicular bisectors into the triangle, it's where they all meet. So that is going to be called the circumcenter for this one. Okay, the special property for that is the circumcenter is equidistant from each vertex. Okay, it's equidistant from each vertex. So let's draw a picture and see if we can get this to make a little bit more sense. Okay, if I have this lovely triangle right here, and I draw in each, I'm going to do this in multiple colors. So if you don't have multiple colors, you can either grab them now or not. It's up to you. So if I draw in each perpendicular bisector, here's one of them. Here's one of them. And here's one of them. Okay? So what does this mean? This means that this point right here where they meet, that's called the circumcenter. That point is equidistant from each vertex. So if I draw a line from that circumcenter to each vertex, each of these red lines, each of these lines that go straight to the vertex are going to be exactly the same length. Okay, so that's a circumcenter. That goes with perpendicular bisector. Let's do our next one. So angle bisector. What was an angle bisector? An angle bisector bisected an angle. What's it mean to bisect an angle? To bisect an angle, we're cutting it in half. Okay, so if I draw in an angle bisector here, that means I'm cutting that angle in half. That's the only thing that it does. If I draw in all three angle bisectors into my triangle, the point of concurrency, or where they meet, is called the incenter. What's special about the incenter is it is equidistant from each side. Equidistant from each side. Okay, so let's draw that. What's that going to look like? Here's my triangle. If I draw in all three of my angle bisectors, there's my angle bisectors. So that means where they meet right here is called our incenter. And that incenter is equidistant from each side. Now remember, when you draw distance, it has to meet at a 90-degree angle. You can't measure a height I'm measuring your height. I can't measure it in a diagonal. So you want to look for those 90 degrees. So sometimes they'll be on that same line, sometimes they'll have new lines drawn. So all three of those pink lines from our in-center are equidistant. The in-center is equidistant from each side. Okay, next one, we have a median. A median cuts the opposite side in half, and it comes from a vertex. If you need to write those words down to have it make more sense with the picture, write down what I'm saying, okay? So it comes from a vertex, cuts the opposite side in half. Okay, does not have to meet at 90 degrees. It can meet at any degree. Comes from a vertex, cuts the opposite side in half. If I draw all three of those in, we have the centroid. That centroid, this is probably the more confusing one, and we're going to practice this one later to make it make more sense. But the centroid is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, let's see if we can get that to make more sense with a picture. So if I draw in my medians over here, cut this side in half, cut this side in half, cut this side in half. Okay, so there's my medians drawn in. Now where they all meet is our centroid. That's this guy right here. Okay, and what this means is from the vertex to the centroid is 2/3 the distance of this whole line. Okay, so let's just cut it into thirds. The easiest way to cut things into thirds is to look at 3. 3 is our whole number. So 2/3 of 3 would mean I have the length of 2 here and the length of 1 here. Okay, if we have 6, well, 2/3 of 6, we could break that down into what? 2, 4, 6. So 2/3 would be our 4. So from the vertex to the centroid could be 4, which means I have 1/3 left from the centroid to the side, which is 2. Okay, and we'll try to make that make more sense when we get to the practice. The last one we have is the altitude. So an altitude is like a height. Okay, we talked about that a little bit, and you'll see that word again. Oops. There's 2 pictures for this one. The altitude is a height, so it just drops from a vertex, drops straight down, and meets at 90. It does not do anything to the opposite side. Now, if you have an obtuse triangle, you can have an altitude on the outside of the triangle, which looks a little funky. If I drop from this vertex and I drop straight down, I have to drop straight down until I hit that opposite side. And I have to meet at 90 degrees. So you could have it outside of the triangle. If you draw in all 3 altitudes, those are going to meet at the orthocenter. Okay, and really the only thing special about the orthocenter is the altitudes meet there. Okay, so let's draw a picture. "90, 90, 90." So here's our orthocenter. Okay, so there's your table. Those are all the definitions that we're going to use. Now I have 9 examples to go through with you. Okay, so let's start going through those. All right, so number 1, the first thing we want to figure out is what definition are we using, and then figure out how we're going to solve. What's that definition mean? Most of the time, we're either setting equal to 90 or setting equal to each other. Okay, so this definition, what do we notice? We notice that it goes through the vertex, which that'll be important in a minute, but what's it do to the opposite side? It cuts it in half and meets at 90. So which definition from our table are we talking about? We're talking about our perpendicular bisector. Now, what happens when the perpendicular bisector comes from that vertex? When it comes from that vertex, we said it's an isosceles triangle, which means these sides are also congruent. So how are we going to solve for x? We're going to set them equal and then solve. So subtract 2x, that guy's gone. Add 7 to each side. We have 10 equals 2x, divide by 2, and x equals 5. Okay, next one. If BE is a perpendicular bisector, solve for AE. So what's a perpendicular bisector do? Perpendicular bisector, go back to your table. A perpendicular bisector cuts the opposite side in half and meets at 90. So, how are we going to solve? If I look at my 2x plus 1, I don't have anything to set him equal to for the side, so that's not going to work. But if I look at my angle right here, that angle I know is 90. So I can take that 5x and I can set it equal to 90. I can solve, so divide by 5 on each side, and x comes out to be 18. But be careful with these because a lot of times they're going to ask for an actual side length, not just solving for x. So if I need to find AE, I'm going to plug that 18 in for x. So we have 2 times 18 plus 1, which comes out to be 37. So make sure you're solving for all of the pieces. Okay. Number 3, what definition do we have? Okay, what's it doing? It's cutting the angle in half. I have these two congruent marks. The angle's cut in half. So we have an angle bisector. Now, when we have an angle bisector, the distance from the angle bisector to each side of the angle are going to be equal. Okay, so the distance from each side of the from the angle to each side of the angle from the angle bisector to each side of the angle are going to be equal. That's an important property to know. So we can set those equal and then solve. I'm going to add 7 to each side. This is gone. I'm left with 12, divide by 3, and x comes out to be 4. But is that all that we have to solve for? No, we have to find SP. SP would be this guy right here. So I'm going to plug that 4 in for x. So 6 times 4 minus 7 comes out to be 17. Okay, next one. So the next one tells you it's an angle bisector, right? So we know we're using an angle bisector. What's an angle bisector do? An angle bisector cuts the angle in half. So what am I going to do to solve? What do I know about these two angles? They're equal. So we're going to set them equal to each other. And then we can solve. I'm going to subtract 3x from each side. Divide by 2, and 38 divided by 2 leaves us with 19 for x. Now pay attention to what this one needs. This one needs TQR, which is the entire angle. So we're going to have to plug this 19 in for each of these guys. We have 3 times 19 plus 27, and 5 times 19 minus 11. Yes, they should come out to be the same because they are equal. This one comes out to be 84. This one comes out to be 84. So what's my entire angle? 84 plus 84 would be 168 degrees. So there's angle bisector. All right, median. So this one we're using a median. So go back to your table. What's a median do? Cuts the opposite side in half. So I'm going to put those marks in. If it cuts the opposite side in half, how am I going to solve for x? What do I know about these two side lengths? They're going to be equal. So we have 3x minus 4 equals x plus 11. And then we're going to solve. Add 4 to each side. 2x equals 15. Divide by 2. And x is 7.5. Okay, now what all does it need? It needs QL. So QL would be just this guy right here. So we're going to plug that x in. 3 times 7.5 minus 4. And what does that come out to be? 18.5 for QL. Okay, next one's an altitude. So go back to your table. What does an altitude do? An altitude meets at 90 degrees. Does an altitude do anything to the opposite side? No. So if it only meets at 90 degrees, you better have that angle set equal to 90, which we do. We have 6x minus 6, so we're going to take that and we're going to do 6x minus 6 equals 90, and then we can solve. Okay, so what did we use? We're using an altitude. X comes out to be 16. Now we need to find ST. Now ST is that entire side length. Okay, so it's this whole entire thing right here. And it does not cut the opposite side in half, so you do have to plug that 16 in for both x's, and then we'll add them together. So we're going to add these all together. Okay, go ahead and plug that in your calculator. What do we get for the whole side? We get 63. Okay, so there's our definitions, that first column. Now we're going to look at our special properties when we have all three drawn in. Okay, so number 7, if AD equals 18 and DC equals 2x plus 3, solve for x and BD. So we need to first figure out the definition of the main lines that we're using. Then we're going to figure out the point of concurrency. That's really what this is, point of concurrency. We'll call it POC. Okay, and then we'll solve. So the first thing that I want to look for is, do we have a perpendicular bisector? Do we have an angle bisector, median, or altitude? So look at each of these lines. If I look at this outside of the triangle, what's happening to each of these lines? I have a line that's meeting at 90 degrees and it's cutting the opposite side in half. So which definition are we using? If we're meeting at 90 degrees and cutting the opposite side in half, we're using a perpendicular bisector. Now go back to your table. If I draw all three perpendicular bisectors in, what's the point of concurrency? That would be the circumcenter. Now, what do we know about the circumcenter? It is equidistant from each vertex. Okay, so what does it give us? It gives us DC is 2x plus 3. It gives us AD is 18. Well, that would be the circumcenter to the vertex, the circumcenter to the vertex. What do we know about the circumcenter to the vertex? They are equidistant, so these would be equal. So we have 2x plus 3 equals 18. I'm going to subtract 3 from each side, divide by 2, and x comes out to be 7.5. So when I plug 7.5 into 2x plus 3, what should it come out to be? It should come out to be 18, because those are equal. Okay, next one. What are we using? So if I look at that big triangle, what do I notice is happening? If I look at each of these sides, nothing is happening, right? So that's not where we need to look. Now look at each of your angles. What's happening to each angles? They're each being cut in half. So which definition are we using? The angle bisectors. Okay, so the next definition, remember, is our POC, point of concurrency. If I draw all three angle bisectors in, what's the point of concurrency called? That would be the incenter. Now, what do we know about the incenter? It is equidistant from what? From each side. Equidistant from each side. Okay, so now let's fill in what it gives us. It gives us that LP is 2y. It says that PN is 3x plus 12. And it says that MP is 2x plus 20. So this one's a little bit harder because we have two variables. Just pay attention to which ones you can start with. But when I look at this one, if I have a incenter, the incenter to each side is equidistant. You should have 90s. So these are all equal. If they're all equal, I need to choose the two with the same variable first to solve. So I'm going to start with 2x plus 20 equals 3x plus 12, and I'm going to solve it down. So I'm going to subtract 2x from each side. We're left with 20 equals x plus 12. I can subtract 12, and I get 8 equals x. Now, how am I going to find y? Well, I know that 2y is equal to both of these other lines, so I'm going to plug that in and figure out what it is. So I'm going to plug it into this one. 2 times 8 plus 20 leaves me with 36. 2 times 8 is 16 plus 20 be 36. So I can take my 2y and I can set it equal to what this line came out to be, which means y is 18. Okay, last example. This is probably the more confusing one, so we'll walk through this one together. Okay, so what am I using first? Look at your sides. If I look at each side of this triangle, what's happening? Each side's being cut in half. Go back to your table. What happens when each side's just cut in half? We're using a median. Okay, if we draw in all three medians, what's the point of concurrency? It would be the centroid. What do we know about the centroid? It is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so the first thing that I would do is I would label all of my pieces in that picture. I'm going to get rid of the highlight. So go ahead and label what it gives you. What's it give us? BG is 2. AG is 8. CF is 9. So this whole thing is 9. All right, so we're going to find basically all of the missing pieces inside this triangle, okay? Now, the easiest way is to say, I know, let's start with AG. AG comes from the vertex to the centroid. So I know that AG is 2/3 of the whole length, which is AD, okay? I'm basically just saying from AG's from the vertex to the centroid is 2/3 of the entire line. So I'm putting that into an equation. Now what does it give me? It gives me AG. So I can plug 8 in for AG, and then we can solve. To get rid of that 2/3, I'm going to multiply by 3. And then we can divide by 2. So AD is 12. If AD is 12, which is this entire line right here, if the whole thing's 12, and this part is 8, what's left over for GD? GD would have to be 4. We just subtracted. Okay? Or if that doesn't make sense, plug it in. GD is 1/3 of the whole length. Well, I found the whole length to be 12. 1/3 of 12 is 4. So there's that one. Let's do another line. The next line that it gives us, let's do CF. So CF, let's find CG first. So CG is from the vertex to the centroid, so that one is 2/3 the distance of the whole thing, which is CF. Well, what do I have? I have CF. I know that the whole line is 9. And if you're not comfortable with fractions, get a calculator, okay? You can do this in your head though. Not whole numbers are always over 1. 2 times 9 is 18. 3 times 1 is 3. 18 divided by 3 is 6. So CG is 6. So if the whole thing's 9 and CG is 6, what's left over for GF? 3. So GF is 3. Now let's do the last one. So now I'm looking for BE. All right, so I need EG. Well, if I set that up, EG comes from the vertex to the centroid. So EG is 2/3 the distance of the whole thing. The problem is I don't have enough information for that. Okay, so we can't start with that. I know BG. Well, what do we know about BG? BG is 1/3 the distance of the whole thing because it comes from the side to the centroid. So if it's 1/3 the distance, now what am I given? I know that BG is 2. So to get rid of that 1/3, we can multiply it by 3, and we know that BE is 6. If BE is 6, this whole entire thing is 6. What's left over for just GE? 6 minus 2 is 4. So that's your final example.